Good afternoon from Berlin. I'm Andrew Curry. I'm a journalist based here, and I'm here today to host the Breakthroughs in Water Diagnosis Falling Walls Circle Table discussion. We have a great panel here today from a variety of disciplines, but all with really interesting things to say about how we can understand water better, where it comes from, where it goes, and what we do to it while we're using it, and then how we can use those discoveries and that knowledge to manage water for the future. Water, probably one of our most precious resources, and yet, even though 70% of the world's surface is covered by water, only half of 1% is actually available for us to use. And we are polluting that tiny fraction, and it's dwindling ever faster as we use it in unsustainable ways. So today we're going to talk a little bit about how we can do that better, what science can teach policy about water use and water reuse. And with that, I'm going to introduce our panel. We have Joan Rose, who's the Homer Nolan Chair in Water Research at Michigan State University in the US. Luis Samaniego, who's the Deputy Head of Department at the Helmholtz Center in Leipzig. And his department handles computational hydrosystems. So he sort of makes huge models of where water is coming from and where it goes. And last but not least, Jeff McDonnell, who's professor of hydrology at the Global Institute for Water Security at the University of Saskatchewan in Canada. Welcome, all of you, to the panel today, and thank you for being here. First, I'd like to go through and let each one of you talk a little bit about the research you do and where you're coming from in terms of this question of water diagnosis. Maybe, Jeff, you can start.
Yeah, thanks very much, and it's great to be with you. My work is in catchment hydrology, so I study the headwaters of large river basins around the world. And my interests relate to where water goes when it rains, what flow path the water takes to the stream, and how long it takes to get there. And this is where most of our river water is sourced, in these steep, often forested headwaters of large river basins like the Rhine, or basins around the world, large river basins. One of the tools that I use traces the stable isotope composition of oxygen and hydrogen that make up the water molecule. And this is kind of a fingerprinting technique. It's used a lot now in paleoclimate reconstruction. It's used to track migrating birds or other biological processes. And in recent decades, it's found its way into hydrology and water resources. And that's one of the tools that I use to understand this water cycling in these small headwater systems. Thanks very much.
Yeah. Joan?
Yeah, thank you. Yes, it's a great pleasure to be here. So I'm a water pollution microbiologist, and I study water quality. And of course, we all know the saying, water is life. And we say that water quality is health. And you already mentioned, Andrew, that pollution is a large problem around the world. And, when I started my career, I thought, well, I'll just go out, take a water sample, go back to the lab, I'll look for my microbe and write my papers. But, when you go out in the field, you start sampling water, you're sampling systems that are important to people. So it's their rivers, it's their lakes, it's their drinking water, it's their beach. And so it became pretty clear that people are interested in what you're finding. You know, what is the water quality? Does it affect my health? How do we fix it? These are the kinds of questions you would get from both the public and regulators and others. So I guess when you work in this arena, you start, you know, becoming very interdisciplinary. You know, the group that, you know, the international group that I'm part of, we have started using DNA technologies. It's always called the CSI of water, where you actually can take a water sample and look for DNA in the water sample and get a signature. We can now look for pathogens and source tracking markers and all kinds of things with this new technology. It's very exciting. You know, we've been looking at wastewater a lot. Wastewater is getting a lot of attention, especially with the Sustainable Development Goals, trying to achieve more treatment and protection around the world. And it's always been part of public health, wastewater capture and treatment before we discharge that water back into the environment. But we're now recognizing that wastewater can be cleaned up and it can be reused. For drinking purposes, it can be you know, reused for all sorts of things. And that's happening around the world. And water quality is extremely important to that, being able to measure that water quality. And so now we're seeing wastewater not only as a public health measure, but as a resource recovery system and a solution really to pollution and some of our stresses around the world. Right now, we're looking at sort of this one water, one health issue. You know, to think about water as a cycle, and to understand that cycle and how humans impact that, and to make sure that the quality is where we want it to be. So I think we're going into this 21st century with some technologies and approaches that are going to help solve some of our problems.
Okay, great, thank you. Luis, maybe you can talk to us about the work you're doing in Leipzig.
Thank you. A pleasure to be with you today. I am an engineer. I study civil engineering, and then at some point, by working at that time in Ecuador, I realized about the pressure of water and why engineers in that time cannot really afford to make good designs for infrastructure. The reason was that we didn't have the data, we didn't have the models. That was what pushed me into catchment hydrology in the beginning, so same description of Jeff. I studied that, and then the challenge for me was, that's great concept, great information, great science have been done. The big challenge is to build models and build tools that allows decision makers to use this information. When I was a student 10, 20 years ago, this was not a possibility. Models were a rarity for universities and research institutes, and it was impossible to address this problem globally. So at the moment, my challenge is to quantify globally the available water in rivers, lakes, let's say stream flow and soils with enough accuracy that can be used for decision makers. And so my interests at the moment are monitoring, predicting, and forecasting floods and droughts at locations and continental level or national level, so that this information can be used at the time that decision makers need, and make it available through source codes that are proved and available for everyone, and use basically the large amounts of data that has been possible only with the developments of the last 20 years. When I was a student from USGS model, the first one I used, PRMS, it was basically extremely difficult to set up a model somewhere. It was a big challenge. That has changed drastically in my lifetime. Yes, and at the moment, this is what takes all the efforts in my group, develop that model and test it basically so that it can be used by authorities or researchers.
Okay, thank you so much. Maybe we can start the discussion by talking a little bit about why we're here in terms of water as a sustainable resource. And I know that we are reliant in some parts of the world on groundwater in a way that is maybe not sustainable. And I wonder if, Jeff, you could talk a little bit about what you know, where groundwater comes from and just how old it is. And then talk a little bit about the concept of sustainability in terms of water, which seems so plentiful, but actually is not.
Yes, well, different parts of the world are reliant on surface water or groundwater, but groundwater use is dominated by agricultural needs. Probably 70% or so of groundwater is used in agricultural production. And increasingly, we're going deeper. And there was a nice paper by Scott Giesecco and Deb Perrone last year in Nature Sustainability, showing for about 11 million wells in the United States, this was a large meta-analysis, that wells are going deeper and deeper each year because the water tables are dropping. And below about 250 meters, most of that groundwater is fossil water, water older than 10,000 years, and as you go deeper, older still. And this is part of the sustainability problem. We're going after groundwater deeper and deeper. Why? Because we're mining it. And I think these are some of the concepts maybe the other panelists might want to comment on as it relates to their areas of research. The hydrologic cycle is quite cyclical, of course, but some of the water in storage is very old, and we're drawing on that water. We're not replenishing our bank account, at least on human timeframes.
Luis, how can you see that in your models?
This is exactly the big challenge we have. The time scales at which the water cycle is happening. That has been a mankind challenge since the beginning of science in the Western Asian civilization. It was only in the Middle Ages that we start understanding the water cycle. And at the moment, what we are doing as modelers is basically encoding this knowledge that we have, the knowledge that catchment hydrologists like Jeff have produced basically over 3 centuries. But the big problem is that everything that is under the surface, it's extremely difficult to observe and quantify. We need properties of the groundwater system, so soil and geological layers, so that we can model. And this is exactly the problem right now. We don't have enough wells to be able to quantify these recession times and how much water can go. And we don't know really what is the time it takes a molecule of water to infiltrate. And the worst thing of all is these molecules might be polluted. So this will enter the groundwater and will remain there for centuries. We just published a paper in Nature Communications, going to be published in the next weeks, that shows the time that it takes in Europe for one of these molecules to really go out of the system again. So what we are giving now at the moment is a huge legacy for the next probably 300 years. What we are doing at the moment is basically contaminating the water of the aquifers. We are living from the capital, and we are not really doing much either to understand this problem or to replace it with a different thing. The mining of groundwater needs to be controlled heavily if we want to preserve our life in the earth. We cannot continue by doing this, especially in the context of climate change, because this is going to be a huge, huge mistake. The weathers and patterns of rain will change drastically in winter and summer, and that will affect this recharge in the groundwater, which probably will make it impossible for the next generations to keep doing what we are doing at the moment.
Yeah, I also think that, we're heading towards a crisis, and we do need to get policymakers to think think about the long term, because this is a long term issue. Even solutions are long term. So even investments we make now, we may not see the results, for 5 or 6 or 7 years. So we've got to be very patient and make sure that we understand the science. And of course, it's this interplace between interface between what humans are doing, what they've done on the land, and then climate that's causing both quality and quantity problems. Certainly wastewater reclamation, where they're using it, for example, in Southern California, where they're recharging groundwater, understanding their groundwater system, understanding their water balance, working with the community, making sure they've got the advanced technology in the engineering system so that they've got a very, very, high purity water to put back in the groundwater system, has helped them with sustainability in Southern California. But we need more of these kinds of solutions. Not one size is going to fit all. And we need the science, we need the data. Then we need to look at these potential solutions. And it means that we're going to have to monitor both the quantity and the quality and gather that information. And like I said, I think we really need to think about these long-term policy solutions.
Well, I want to come back to the policy solutions, but I'm curious about the data itself. And all three of you collect different kinds of data, but it seems that one common element is that the ability to analyze it has come a long way fairly recently. Well, maybe you can just tell me, what are the biggest breakthroughs in your area that have made possible the knowledge that you have today? And is there anything, once you think about that, is there anything that you think is sort of the next wall to fall, so to speak, in understanding what's going on with water in that aspect?
Well, in my area, stable isotope tracing of water, tracing the oxygen and the hydrogen that make up the water molecule, that really came about with the discovery of the isotopes of oxygen and hydrogen back in the 20s and 30s. And the implementation of that with the kind of things Luis was talking about, following the water molecule on its path from how it infiltrates the ground to recharges groundwater to ultimately appears, let's say, in a river, has really revolutionized our thinking. In the last 15 years or so, devices to make those measurements in laboratories has been revolutionized. Something called the laser spectrometer has put these tools into the hands of mere mortals, meaning hydrologists. And this has really increased the spatial and temporal analysis of this. But I think I just want to make one quick comment more broadly in hydrology. I think we have a feeling as a tax-paying public, particularly in Western Europe and North America, that we monitor these things very well. And in some ways we do. Our river monitoring is pretty good, but boy, the amount of water in storage and then the rainfall or precipitation measurements we make are very poor. And this is a problem for even our climate models. If we can't get the input right, that is precipitation, how are we going to get all the other things that follow on from those inputs? And I think this is the greatest uncertainty in our models. Luis might disagree, but unless we get the input right, getting all the outputs, whether it's quantity or quality, is challenged. So I think still some of the basic measurements are our biggest Achilles heel in advancement. So probably measurements will be what will really help us in terms of improving our estimates of change.
And is that a technical challenge, or is it just an interest and resource challenge?
Yeah, I look to Luis on this, or Joan.
Probably both.
Yeah.
I can add a point on Jeff and answer, please, if you allow me.
Yeah, please.
So I can give you basically how it was when I started a German model for predicting soil moisture and stream flow. 2010 basically was not possible to get all the data we need to get the rainfall that has been collected by the meteorological office. What was the goal? The goal was the law, that this publicly available data that should be available was not available unless you pay a fee or you pay a certain amounts of money or you have a special project. This is open should be open. It was open years later, and now this has revolutionized the hydrological modeling. When I was a student, we only work in little catchments in Germany because we need to have a project with the local authority so that we can get the precipitation data. Germany is one of these places in the world which collect information in a massive amount of density and fantastic information, even going back to the 1700, the oldest measurement in Potsdam. But this data was hidden behind walls, basically. And by a change of that law that allows us to get into this, we could develop a system that is now running. It's the drought monitor in Germany. And other countries in Europe follow this. And now we can have, for example, precipitation data, which is exactly what Jeff is saying. If this data is not available, then land surface models, which are the basis for climate models, cannot calibrate and parameterize the convective rain schemes. And we are doing basically in some places not that good because this data is not there. In other locations, and this is enough research on this, we have seen a decline of measurements in precipitation globally because of the costs and because of the politics related with water. And so if we change this, and I'm sure we could basically get into a next level of the modeling globally. But we need a specific commitment from everywhere so that this information is available over all continents, and especially those continents who invest less in collecting should also get support and training how to do it. It's extremely valuable to get the basic information so that we know how to make a decision tool. A model is as good as the data we put in. If the precipitation is bad, we cannot get basically enough accuracy for the model to be useful in decision making.
Is this a really to give lesser developed nations or parts of the world that don't already have the capacity to collect that information? Is it expensive to set up these water?
Yes, well, it is. Each station costs about certain thousands of euros, and then the really big trouble is to maintain them, keep running, and then have an homogenized network. That's why only rich countries in the world can handle this thing. USGS handled very well. That has an example that then they really, when I was doing the studies, we moved to US to do the studies because the data was free and we can just go in the USGS and download it. In Germany, it was a disaster. We couldn't do it. But nowadays has changed completely. Now we are doing the same thing and asking through organizations in Europe to get the same kind of idea for other countries who are still protecting the data because they think they have to protect, when in fact it should be open. And only by liberalizing, taking these walls down, then researchers and practitioners and engineers can take this information. It's extremely expensive, and I think this is something that the states have to invest. But if we don't invest on this, we will have bad chances, or very little chances to make models for the local decision making.
And we need those. We definitely need those models if we're going to assess at these various scales, both time and space. Global and these long time periods. What's going to happen? As poor as quantity is around the world or scattered in terms of the data, quality is even worse. So if you talk about water quality, what are you talking about? Are you talking about nutrients, phosphorus and nitrogen, which is affecting eutrophication around and algal blooms? Are you talking about waterborne pathogens like what I study? Are you talking about other chemicals, industrial chemicals, or natural pollutants? So the data on water quality is very, very poor. It can change in time and space in some cases quickly, like at a beach, or it can be very recalcitrant in groundwater systems. And we do need models, and rainfall drives that. We already know that rainfall on the land drives the transport of these pollutants to sources where humans are exposed. And so ultimately, we're going to need more information, more data to produce these models that will help. the technology in the water quality arena, at least for pathogens and microbes, has been polymerase chain reaction, PCR, we call it for short. And it's basically a way to copy the DNA in water. And we can design this little copying machine, so to speak, to look for any pathogen or any organism of concern. And we know that these pathogens show up when it rains. That's when our outbreaks occur around the world. These major plane crashes for communities where their water becomes contaminated and you have a large number of people sick, you have a large number of people even dying, is associated with these rainfall patterns and the washing of these pathogens into our water systems. So this technology has been extraordinary, and it's just now making its way into the water quality arena so that we can get more analysis in time and space for more specific pathogens of concern. Knowing where the pollution comes from, knowing which pathogen is there, and then tying it back to these models is going to be extremely important to actually have water quality models tied to the water quantity models.
So it seems
And
like
I would
go ahead.
No, sorry. I was going to say I would bet that in Western Europe or even in the US, with some of the best precipitation monitoring, you take these rain gauges and you put them all together next to each other. They might fit into 1 or 2 football stadiums, and that's their distribution across Western Europe or United States. So we have this issue of data density and how we interpolate and maybe miss a lot. I think it's also an issue in the Indian subcontinent. I was involved in an all-week meeting last week in India, and this was their defining issues. They're collecting data, even though it's not going to be at the density or perhaps quality of Western Europe or the United States, but the researchers can't access it. Just like Luis was saying, they have to pay for it. Their budgets for research are low, and it's effectively hidden or removed from the researchers that could make use of it. So yeah, in terms of falling walls, I think free data access is it for at least on the hydrology side. Yeah.
And just so I understand, what is the motivation for governments who are paying to keep the data or to collect the data? Is it that they want to sell it commercially? And
I can tell you how was the law. And basically in the weather service in Germany was written a paragraph that the agency needs to finance a certain percentage of their budget has to be obtained by selling data. That was the paragraph. They were not doing anything wrong, or that basically that part of the law was there. And because of this, they charge a certain amount. But for a researcher, or for when I request the first time, could you please give me the 3,500 gauge stations from 1950 to now daily? They reply, "Are you crazy?" So that was the answer, because this will cost you millions, they told me. And then things started happening. 6 months later, I got all the data and for free. So that was basically the revolution for my life. It was the changing from doing hydrology with 200 basins in the south of Germany, where I started, to do hydrology with 3,000 long-term stations. We have 5,000, but they have a broken rain series over the war. But there are still some stations even during the war that have observations. And that is extremely valuable data, but was hidden because of this paragraph. So that was the thing. And there are other problems, this organizational problems. Some of these data sets belong to the local states. We have a decentralized system in Germany, and probably other places in Europe are the same. Each state has its own way of collecting data. So this has to be homogenized. And I think at European level, this is basically at the moment going quite well, using, for example, Copernicus Climate Change Service, who is collecting data, and they are going to have a portal where all this information is now publicly available so that any person in the world can collect. This is an amazing change from what it was hydrology when I started doing it. In that time, even getting a Landsat image was a nightmare when I did the first time. I had to pay in that time a lot of money to get one, and I got the raw data. I have to classify it by myself. Wrote the first paper with this. It took me a while to do. As a PhD student, do a catchment study took a lot of time. Nowadays, you go to Google and you have the data. So this is a revolution. It's a revolution in our lifetime. And I think people should understand that. So our aim is at the moment, make this data, process data, so that, and we put models that analyze this data. We aim to have over the whole globe, our model and other models using the open available data so that any student can pick a coordinate, delineate the basin, and get something to start working in 20 minutes. That will change and distribute and make the data fair and make sure that the next generation of modelers and hydrologists and planners have first something to decide. It's like a medical doctor not having temperature. You cannot make a diagnosis of what's happening in a place. If you are just hidden, you don't know, you are guessing. Like the engineers I was working in Ecuador 25 years ago, we were guessing what's going to be the amount of water in summer. Well, if it's a guess based on extrapolations from other locations, you can miss the point. And that's the thing that happened. They missed and they overestimated the costs of infrastructure with the prejudice for the people. And then agriculture suffered and everything, the infrastructure, the economy. And I think this is what was happening is still in a time when we could still understand what the weather is doing. At the moment, the weather is changing so fast that we have seen in our lifetime already drastic changes in the way that the weather and the patterns. And if we don't have this data now, and we don't have the tools, well, doing hydrology from the hydrological, from the engineering point of view will be quite difficult, quite challenging in the next 30 years.
Let me jump in. You said things started to happen, and then 6 months later, you had the data. In terms of as scientists talking to policymakers, that those 4 words, there's probably a very long story behind things started to happen. But what do you all lean on when you communicate the work you're doing, and how do you get these changes made? It seems like
in my case,
I think the climate change, arena, the global, a global effort of scientists coming together along with governments to talk about, global climate change is a good model for us to follow for other data. The investment and the return on investment is now quite clear for governments in terms of planning and that type of thing. But it took a while to get there and to then produce a database that is maintained. Maintaining databases and the quality control of those databases is not easy. But I think there's a recognition there now. Water quality is so far behind, and there's still some political issues where, you don't want your poor water quality, your polluted water, to be seen on the global stage. When there's global businesses trying to move in and they say, what's the water quality in this city or this place? If I want to expand, globally around the world, what's the water quality? And they don't know. And there's still some politics around there. And it's very hard to get global databases on water quality. Even things that we might measure, nutrients and things like this. But this is the way we have to go for the future. And I think what the hydrologists have done, and those that work with the global climate models and that type of thing, is a model for us to adhere to, coming together as scientists around the world, coming together with policymakers.
Jeff?
One thing, Joan, I'm wondering if this has happened in the water quality community. In Canada, we've been able to work with policymakers when we cast it in terms of economics. So we had a flood in Western Canada 7 years ago, the Calgary flood. It was Canada's largest insurable disaster, that flood. And half of Canada's largest insurable disasters in the 20 years prior to that were droughts on the prairie, because this is our breadbasket, if you like, for Canada. So when you start to put floods and droughts in that context, boy, people listen. And I wonder, casting the water quality piece of Flint, Michigan, or other, well-known disasters or issues, if that is a way perhaps on, your side to frame things, because it's been quite effective, I'd say, at least in Canada and in Europe, putting it in that context.
Yeah, it's definitely, resource economics, especially for quality, needs to come a long way. We
Yeah.
need to interface with that discipline for sure. But it is there. We do get costs. And it's sort of costs after the fact with these disasters, and then getting the benefit of preventing them. That is where we need to work on, is show that economic value, economic vitality of a community. Because you have high water quality. They do a lot of that in the Great Lakes region. So we understand in the Great Lakes region, we have one of the best, actually, between Canada and the United States, water quality agreements around the world. And it's not just, it has teeth, right? It really has teeth. So this water quality agreement talks about monitoring. It talks about what we should be doing to protect and also restore areas of concern where pollution in the past has come forward. So we do have these models, we do have some economics. We don't really have global databases on water quality that, and maybe even global models that we could start to adhere to, because of course it's tied to water flow. But I think it's very important that we do that. We do know, like, for example, what's the cost of a beach closure or an outbreak, which is a very costly event associated with these pollution events to the community and to the region. And so, that's an area that needs more exploration. We need more resource economists to work, with the water professionals.
Okay. We have about 20 minutes left, and I'd like to encourage anybody who's out there watching to chime in. If you have questions, you can write them in the chat function on the side of your screen, and I'll pass them on to our panelists. This is a great opportunity to tap their expertise. And in the meantime, with the focus on climate change and these sort of climate-related stresses, drought, floods, when it comes to water, are there things that we're missing in terms of major problems, population stress? Joan, I know you've been looking at new diseases, new organisms, in some cases very new. What aren't we paying enough attention to with necessary but still kind of overwhelming focus on climate change?
Yeah, there's climate migration right now that is a problem, and means, and it's not just driven by climate, there's political migration and other things happening. And all of a sudden we have settlements in areas that don't really have access. They don't have access to sanitation, safe sanitation. They don't have access to safe water. The one thing this pandemic has shown a light on, this COVID pandemic, which it's been an extraordinary year, is that we are not, we tell everyone, well, you've got to wash your hands, you've got to have good hygiene, and then part of the world has no access to water, enough water for hygiene or water safety. And on the wastewater side, around the world, I mean, it's been amazing. The profession has come forward, both from the industry itself and from the water quality diagnostics global community, to monitor for SARS-CoV-2 in wastewater, actually monitoring the health of our community by what's happening in the wastewater. And this is an opportunity to really create a global approach to data management, to linking what goes on with water use, and our health. And I think that we're starting to see how this is a great opportunity, but all this suffering, good science, if we pay attention and we won't let that suffering go to waste that's going around the world. We can make a change. We can make a difference by monitoring and gathering this data. So I truly believe that the profession, the water profession, and those working in this arena are trying to come together to do good.
To turn the crisis into an opportunity, so to speak.
Yeah, and not waste, whenever there's a crisis, whenever there's a problem, a mistake, if we don't study those mistakes, if we don't understand what happened, obviously it could happen again, but we can also learn something that really can help communities and public health around the world.
Jeff?
Yeah, maybe in terms of your question, what we're not paying attention to, there's a great recent book, Uninhabitable Earth by David Wallace Wells, and it talks about these issues of climate migrations or climate refugees, I guess. In Canada and in northern climates, cold places losing their cold is really a defining issue. This is the change from snow to rain in high elevation precipitation. It's how, through the Andes, again, Luis, coming from Ecuador, perhaps originally, I think, Luis, are you from
Yes.
Ecuador originally? Yeah, I mean,
Right.
Cities, that might rely on glacial melt for their summer low flow, like Santiago, Chile, for instance.
Mhm.
Oof, they are in a world of harm with that piece going away. In Tibet, the Tibetan Plateau, there are enormous resources being spent trying to understand how that region is losing its cold and what that will mean for the headwaters of many of the world's large rivers that flow through either China or India. So I think this is something that many groups are looking at on the water side. This loss of cold and what it might mean hydrologically in terms of, again, floods, droughts, and probably water quality also.
I think that's a great point. I think from the layman perspective, people imagine Canada as a climate change paradise that we're all going to just move north. But it's a much more complex world than that.
One comment on this, Andrew.
Yeah.
Well, there is a lot of things happening. People is losing water, glaciers are disappearing. For example, I can say all the cities in the Andes are having this problem, but Spain or Germany is the groundwater recharge, which is missing, and in winter, and that will create a problem either with floods or with recharge of groundwater. And you can list lots of things, but then what we need to do as a scientist is to make tools that allow decision makers to take decisions right now that will affect human beings in the next 40 years.
Mm-hmm.
And what's happening is that all these anthropogenic effects are not yet well built in models. And this is where we need to put a lot of effort at the moment to improve the parameterizations that are dealing with these anthropogenic changes and make the next versions of these large models that are creating ensembles that allows us to understand what is going to happen, to have the possibility to assess these human interventions that we have been doing or we have done. This is a large challenge. I remember, for example, a big, nice book from Jim Duke. He said in 1982 already, parameterization of hydrological components in GCMs is an unsolved problem. Well, I can tell you with lots of literature listing that this is still the case. We have a big trouble to do good hydrology in that kind of model because there is a discontinuity between what the community is doing in the atmosphere, what the community in hydrology is doing. This is another wall, barriers that we have created across disciplines. The way how meteorologists work is communal, so community land models and community-based codes, so that we can really do large, they could do large efforts and progress. whereas hydrology has been basically, because of the data conditions, working most of the times locally. And now there are many tools and many teams that are building up global models, but still suffering from the old diseases that is basically the bad of parameterization, the lack of little processes that we need. So we need to basically do lots of efforts to improve that and include human and make these land surface models part of the GCMs, of global models, to reproduce, for example, stream flow and water quality. We don't have any GCM at the moment doing that. And why? You can say, why? Are not yet up to the task? Well, Joan says very clearly, we don't have groundwater. We don't have data for nutrients and pollution globally. So, and we don't have even stream flow generated directly from a GCM. It's at the moment a post-process. So, ECMWF will be probably the first agency that will have on routine basis generation of runoff on the forecasts, because they are building now a global model at enough resolution that could be used for national planning. That will be a revolution. This is for me a falling wall again. The next step is to improve these models, go even lower in the scales, achieve what, for example, Eric Wood and others already published 10 years ago. Make these models at high resolution with the possibilities to quantify uncertainties. And that will be the only way. Going in this high resolution modeling with enough ensemble members that we could do with the statistics so that local conditions can be reproduced, and then probably decision makers can take this data. The next level is make this data accessible. Luis, so it's a full combination of activities that need to happen in the next decade.
Okay, we have a couple questions from the audience, which is great. There's one that I'll come back to about modeling, but Joan, somebody would like to hear a little bit more about how much progress we've made in terms of reusing reclaimed wastewater, and is it something that people are doing on a regular basis? And kind of, can you give us a couple examples of best practices in wastewater reuse?
Sure. Yeah, it's growing around the world as a potential solution. And Singapore is a very good example where they began 20 years ago thinking about their limited water resources for the growing population there. Now they've become a hub for wastewater reclamation and producing purified water that goes back into their water supply, then gets treated by routine drinking water treatment. And of course, I mentioned Orange County, which has also been a leader in developing technology to produce purified water. And it's not just the engineering technology, it's the monitoring technology that goes along with that. The sensors and more data on which processes remove which contaminants, so that you do have a water quality that is of the highest nature. And you can get rid of many of the contaminants that might come into wastewater. And so, yeah, it's happening around the world. The Sustainable Development Goals actually have a sub-goal for countries as they start to look at building sewers and building wastewater treatment systems to think about reclamation, because it won't cost that much more to add on a reclamation system. And so they're looking at it in India. Of course, it's expanded in the US from Virginia to Seattle, even, Seattle and Oregon and places where you would think they're water rich. And it's either driven by stress, obviously water stress. You don't have enough water, or you can't bring more water in that's sufficient for your growing community. Or in some cases, it's also because of pollution control. So if you take a lot of little wastewater plants that aren't working very well, like they did in the Occoquan Valley in Virginia, and put them in one larger advanced wastewater system with good treatment, you now produce good water for recycling, and you've reduced pollution around the region, around the watershed. So it's been growing both because of engineering technology, because of need, and the ability to monitor the quality and provide that to the public, quite frankly, because it's the public ultimately that's going to say, this is acceptable to me to move forward with reclamation and resource recovery.
Is that the big, do you think public acceptance is the big barrier in places like Europe, moving this technology? Because yeah, I mean, you're not talking about gray water just used for irrigation. You're talking about people drinking.
Yeah, black water and yeah, everything we put down into the sewer, and people know what they put in the sewer. And so there is an issue with public acceptance. And, you know, originally you try to explain the technology, the engineering technology, like reverse osmosis membranes, like what gets through those membranes, and try to explain it. But ultimately what the public wants to know is, are you monitoring the water? And what are you monitoring it for? So you can imagine how public confidence might be if you've got one data point for one analyte, and how that public confidence can grow if you've got thousands of data points and thousands of different chemicals or microbes that you've monitored for, and you show that to the public. So ultimately the public wants to know that somebody's monitoring the water quality and that they can see what's going on. And there's quite a good acceptance of it as when you build up that knowledge. And again, it goes back to this data, you know, having the right data to share with the public.
Are the standards fairly uniform? I mean, are the expectations in Singapore the same as they would be in Berlin?
So there's not global standards, but there's global goals by the profession. But each country kind of puts in their own policies. I think that, you know, having groups like the European Union, which kind of oversees what goes on amongst different countries, can kind of harmonize that. And I think, Luis, you mentioned trying to harmonize these things. It's very important that we do that. In the United States, it's our drinking water standards that guide drinking water, whether it's wastewater reclamation or not. But in some states like California, they've been very stringent. If you're going to use, you know, if you're going to have wastewater reuse for drinking purposes, it's got to go beyond just our drinking water standards. So we need to harmonize that kind of approach. And I agree with Luis and that's going to advance our science and advance our ability to really solve the problem.
Homogenization is fundamental. That is the Water Framework Directive that the European Union put in place, and this is a law. So it standardizes these thresholds in water quality for a bunch of thousands of chemicals that needs to be prescribed in law so that people can take care of this and they can charge companies who are polluting more than that. And this is fundamental. Without these laws, we cannot have an homogenization across a continent.
Last question, and I'm not sure if it's more for Luis or Jeff. What do you think about the access of good quality digital terrain models in terms of improving the quality of surface and groundwater models?
that is, I can tell you about this thing. My first DEM I constructed by hand for a little catchment in Ecuador, and it took me 6 months to do it by hand. I have to digitize the whole thing. In that time, the topographical maps were hidden in the military institute. So it took around 3 months to get letters to get the topographical maps. So if you don't have this data, you can't really do hydrology. It was because of the NASA commitments that we got the first DEM across the globe. And I think that was a revolution. And later on, come now the new Terra ML from the DLR. And this is going up to the meter level. So without these products, we would not be sitting here and telling you that now it's possible to do some modeling. That was fundamental. That was a wall I suffer in my career. I spent 6 months of my life digitizing a map to get a DEM. And the students of today don't need to do this. So someone has to do it, and then probably things happening. This is extremely valuable information. Same to DEM is the soil maps. Fundamental data that you need to have. It has to be, again, homogenized. The World Agriculture Organization has And so the FAO, Food Agriculture Organization, has homogenized. That was the first soil homogenization that exists, but it was too coarse, and nowadays exist better models, and so on. So this information needs to be homogenized. Now we need geology, we need all the data that exists, and is sometimes locked indoors somewhere, put together and released for the public and for the science. When that happens, you will start seeing changes. So I would basically love what they did in that time.
Okay.
I might just add briefly to that, Andrew, if I could, that
Please.
I think Luis is right that it's been transformational access to digital elevation data. But our big challenge is what lurks beneath the surface. So the surface is very well characterized. What lies beneath the surface is very poorly characterized from a water inventory point of view. And I think that's really the next wall that needs to come down. How to illuminate that black box of what's beneath. Work by Barbara Sherwood Lawler at University of Toronto has been identifying billion with a B year-old water in groundwater wells in Ontario and in South Africa. How do we understand the science of water cycling and hydrology when it's unobservable largely underground? And I think the same revolutions in satellite measurements for terrain need to come for subsurface, and a lot of gravity-based work with GRACE, a satellite that's used by a large community. That's been really transformational in terms of showing how systems are storing and releasing water at kind of global scales. But that's really a frontier, I think.
Last comment, and then I think we're gonna have to wrap up. Luis?
Yes, again, going back to GRACE, and I'm really fortunate that it was also a community that organized this thing. It's just two institutes, one from GPL and GFZ from Germany, who put this together, and now we are in a following mission. That has been transformational. I fully agree. That has been one of the most reasonable and useful products to check the climatology of land surface models and climate models. And this is going to be long enough. Now we have 10 years of this data, and hopefully the next version, which goes up to about 10 kilometers cell size, will preserve again over the next decade and will allow us to make this observation that was hidden. The problem from groundwater, I said, the soils, is that we don't see it. So if we don't have sampling, we don't know anything. And this is a black box. And I think traces, and I think that's the work that Jeff has been doing. If we do this, perhaps illuminate a little bit and put some light to what's happening below the surface. That has been, and I think I fully agree with him, this is the next wall. We need to illuminate that piece. At the moment we are just blind, we don't know, we make a black box in our models and we suffer from this. But it was, again, that was the case 20 years ago. So I don't think that in 20 years we will sit again in this table and see what happened during the time. I am sure it's going to be a big change in the ground observation.
Well, I want to thank all three of you. It seems like, for me anyway, one of the big things to come out of this is A, the importance of data, but B, how important it is to make that data free and available and accessible to people all over the world if we're going to solve this crisis of water as we move into the future. I
forgot to mention cosmic ray technology, for example. This is something that probably revolutionized soil moisture monitoring globally. If we built a network with these sensors, cosmic ray is, the neutrons are there, it doesn't create, it's neutral, it's a passive observation of nature, and it gets information of the top subsurface, and that is for agriculture fundamental. If we make this commitment, that's the beginning of trying to put some light on the underground.
One last point, I think that you both made is that these organizations, these global organizations, the UN, FAO, bringing groups together, like the Global Water Pathogens Project is coming together. That's the start to try to get, interaction at this higher level and make data, develop a database and make it available for these global maps.
Yep.
Right.
Well, with that, I think we have to close. I want to thank all three of you so much for your time and your expertise and your decades of hard work on this important subject of water. And thanks to the audience out there for listening and for coming in with your questions. And also thanks to Falling Walls for putting all this together and making it accessible via their website, www.falling-walls.com. If people want to come back to this later, or if you want to spread this discussion to your friends and colleagues so they can listen in too, it'll be available afterwards on the website. Check the website too for the next discussions from the circle and also some of the breakthroughs that people are talking about on an individual basis. And yeah, have a great day, evening, and thank you all so much for being here.
Thank you.
Thank you very much.
Thank you,
very much to
Andrew.
all of you.